gluing, factorizations, etc. And their work is a physics article, and it was fairly quickly translated to the notion of a modular tensor category and a modular functor. Effectively, Moore and Seiberg, not mathematicians, but not that much mathematicians, discovered this notion of modular functor and modular tensor category. That was then used for completely different areas like topology, invariance of knots, and so on. But one could take this as a guiding principle, in particular for vertex algebras. If you can prove that your representation category of your given vertex algebra is a modular tensor category, then in some sense that reconstructs the corresponding conformal field theory, or better said, at least its bulk space of states. And then for example, you could also have fusion rules or some data. Okay. And that's it with this. But rational conformal field theory, as you probably all know, we don't talk about that too much anymore, right? I'm not sure how many. Anyway, when I started to study these things, one was always talking about logarithmic conformal fields. Logarithmic because correlation functions might contain logarithmic singularities, and that's intimately connected to a non-semi-simple action of the Virasoro zero mode, so in particular to non-semi-simple representation categories. And one is very much now interested in kind of making the VOA theory of logarithmic conformal field theories somehow rigorous, and that turns out to be difficult, to say the least. So if I would recall the history, already in the late 80s, there was work by Virasoro, who's not here, and Rosansky, and on the Westover-Witten theory of GL1/1. And that is an example of a logarithmic conformal field theory. Then in the 90s, there came these so-called triplet algebras, and they were all mostly studied by physics. And then beginning of 2000, Azad and others, right, Alyosha Semikhatov especially, they started to study this triplet algebra more seriously. And also in the 90s, say if you open a textbook and you and it wants to give you an example of a rational conformal field theory, then the first example that will be given to you will be a lattice vertex. I mean the free boson conformal field theory, so that corresponds to the compactified on a torus is then that corresponds to a lattice vertex algebra, and then the second example will immediately be an Westover-Witten theory. So a conformal field theory associated to a simple Lie algebra, and the level of the corresponding affine vertex algebra will be a positive integer. And so the most natural thing to ask was, what happens to these Westover-Witten theories if the level is not an integer, it's a rational number? So it was then called fractional level Westover-Witten theory. And the problem was that the people who studied it applied the techniques of the rational conformal field theory to something non-rational, and then a huge zoo of misconceptions arose. In particular, I think if you open the book by Di Francesco, Seneschal, et Mathieu, and you look at this short paragraph section on fractional level Westover-Witten theory, what do they say? They are physically sick, physically, intrinsically sick, something like that, right? I think so. And that is more because it wasn't, but I would say they are totally fine. I thought about what I'm going to present. I will only present as two here to make it very clear what happens. I hope that's okay. Anyway, okay, so that was a bit blah, blah, blah. And now I'll tell you what a VOA is. It's the following. You probably know this. It has a data. V is a vector space. You can also take it as a superspace. It doesn't need to be complex over the complex numbers. Then we have a vacuum vector, a translation operator, and you have a conformal vector that one usually denotes by omega. And then and of course you have fields. We saw that in the last lecture. Fields for us is a map from the vector space to endomorphism valued formal power series. And then you ask for some axioms, and what you want is that the field corresponding to the vacuum is just the identity. You want the translation operator to act as a derivative. You want the field corresponding to the Virasoro vector is the Virasoro field. Just write Virasoro field. That means it has the operator product algebra of the Virasoro algebra at some central charge. Then you want a state field correspondence. We also have heard about this in the last talk. So that means if a field acts on a vector, we get a formal power series with coefficients b, and it is supposed to give you as the leading term your vector back. And then the most important axiom is locality. Locality tells you that you want your fields to almost commute or to quantum commute, and that means so if I just wrote here 0, they would commute, and we would get something quite trivial, which called commutative vertex algebra. But if you relax this, that the commutator only vanishes if multiplied by a sufficiently high power of z minus z prime, then you get the locality axiom. But I'm probably telling almost nobody here anything new with this. The point I wanted to make is that the locality is the heart of the definition. It is what defines an operator product algebra, so the algebraic structure of the vertex algebra, and but it is completely formulated in terms of formal power series, and that's maybe not the optimal formulation. In fact, there exist 3 equivalent formulations of the locality. Another one is via Jacobi identity, which is even less instructive. Actually, that one is quite instructive. And then there's a third one via correlation functions. So we take V prime denotes the dual, the graded dual of a V, and we take a vector V prime and V prime, and now let's take 3 vectors in our VOA. Then we can look at the pairing of V prime, and now I take a field associated to the first vector and to the second vector, let it act on V. But what else can I do? I can swap the order of the 2. First act with the vector corresponding to the first vector on V, then the second one, and then do the pairing. Or I can convolute this. I can look at the field and insert here I can take the field corresponding to the first vector acting on the second vector and then act. And so then I get 3 expressions. And one requires that these converge respectively in these 3 regions. So the first one in this region, the second one in this one, and this one, and that they absolutely converge in these regions to a certain rational function in Z. Z and W.
So in your second expression, where is Z?
Oh, there is the last one. Why you want put
Say
Z
it
at
again.
top?
Second.
Second. Yeah, that one.
Oh, yeah, thank you. This is Z, thank you. Yeah. Always U1 comes with the Z and U2 with the W, except here you insert the difference of the two. And it turns out that locality is equivalent to that these three converge to a rational function to a common rational function in their respective domains. And this rational function has with only poles only at Z equals W and at 0. Now, these expressions one would call correlation functions. The correspondence between these, the first two is a commutativity property, and the last one is an associativity property. Now, why does one introduce this? See, what is a conformal field theory itself? What you there you don't have your complex variable Z, but you have a Z and its complex conjugate. And you think about it that you have two vertex algebras acting on it, one completely in the holomorphic variable in Z, and the other one completely in a Z bar. So what you would like to do is now you would like to do replace V, let's say by H, and that's just a change of symbol, H for like space of states. But in particular, you would like to replace NV, so formal power series with anamorphism valued coefficients. You still want to keep the coefficients to act on your space of states, but now what do you want to have here? So I want still to have I want to have two formal variables, which I eventually then identify in the correlation functions as their complex conjugates. But then you want, for locality, I can also have any arbitrary power of the absolute value of Z, which is then here indicated with this R to the R. And then what else can one have? One can also have the logarithm of the absolute value here. And if you do this replacement, you effectively keep the axioms of the vertex algebra, but with the notion of locality in terms of these correlation functions. Then via this replacement, this gives rise to the notion of a full vertex algebra. So that means there exists some structure which really mimics now the full Hilbert space, the full conformal field theory. Now, if you look at the literature, you'll almost find no article on that. This has been recently studied quite a bit by Yuto Moriwaki, and he'll be here next week. So he can tell you more about this. And Yiji Huang has introduced this under the name of meromorphic vertex algebras. I think it's essentially the same thing. But it's kind of a bit a sad story. See, this is here now conformal field theory conference, and vertex algebras were introduced because of a conformal field theory. But really, if you look at the literature, vertex algebras have many applications and are fantastic tools for many problems. But the connection to CFT is almost completely neglected, and at least recently. Now, one problem is also because it's very difficult. So I tried. So okay, Yuto had this definition without the logarithm, but adding this logarithm to the definition is no problem. And then I tried to find a single example, and I managed after hard work to construct one such full vertex algebra, namely the symplectic fermions. I'm not giving the construction because it would just be very technical. So one kind of needs a good way to go to full vertex algebras, and my take is actually you have to do vertex algebra representation theory for quite a bit until you understand the representation theory good enough, and then you go to a different technology, because different technologies will be more powerful. And this is a little bit what this conjecture goes to. So I take a VOA V, and let V braided tensor category. Then the belief is the following. So we have full vertex algebras. So the thing that should formalize on an algebraic level logarithmic conformal field theories. And now I of course have to relate this course somehow to this representation category. And so, well, the full vertex algebra wants to be a module for 2 copies of the vertex algebra. So this is why I write here rep V times rep V bar. The bar wants to mimic the complex conjugation, the replacing of Z by Z bar. And what the symbol means is the category is a braided tensor category. The braiding is a choice. The inverse of the braiding would be an equally good choice. The bar is just that I choose the inverse. Really what it means is if you take parallel transport of fields once around another, you change your orientation. And the conjecture is that there's a 1-to-1 correspondence between this one and commutative algebras. In the same category. Okay, so this conjecture is at the moment, of course, very hard to understand for you because we haven't had this background here, but we have Chelsea. And Chelsea will also give 3 introductory courses. And it has really been the success story of vertex algebras of logarithmic conformal field theory. as really being the story of the interplay between the theory of, let's say, braided tensor categories and the representative theory as such of vertex algebras. I think Chelsea hopes that she will explain what a commutative algebra is. Is that correct?
I'll do algebras. I don't know about commutative.
Commutative is algebra is already very good. Yeah, this conjecture I think is not deep. I just didn't have the time. And it's actually motivated by something very similar that has been done by Juan Klipowski. So this conjecture in particular is extremely likely. And
so can you see this? Can you check this conjecture in a case like the non-diagonal minimal model?
Can you say it again?
Can you check this conjecture in a non-diagonal minimal model?
Yeah. So for example, it's true for all SL2 best domain written modular invariants. So also for the non-diagonal, especially for this E6, E7, E8 type one. So yeah, can I check this?
So what's commutative algebra for that case, or SL2 case? What is a commutative algebra that comes with it?
Yeah, for these exceptional invariants, you mean? Okay. Another condition of conformal field theory is that the partition function of the Hilbert space is modular invariant. Now, what people have done is they have looked at the Westominer Witten models of SL2 at positive integer level, where modules, characters, etc. are well known, and so then they have elaborated all modular invariant potential partition functions. This is called the ADE classification of Ditziksen and Zuber, end of 80s, right? And they have found that there's the usual diagonal modular invariant. So that would be just schematically a finite set of simple objects indexed by some index set, and it's just the diagonal one. And then that was identified that you had for every positive integer level. Then you had a diagonal. Then you had a D-type modular invariance, and those you don't have for every level, right? You're only for even level or odd. I forgot, but they correspond to the simple current extensions. So depending on if how I can tell you if k is equal to 2 modulo 4, then you have an honest simple current extension, and then but I think it also worked for mod 2. It's just a bit more complicated. And then you had 3 exceptional ones, and they were called E6, 7, 8 because they reminded you of that. 2 of them were easily explained via the conformal embedding of SL2 at level 10. So 10 plus 2 is 12, the dual Coxeter number of E6 of SL2 at level 10 inside SO5 at level 1. And then the E8 one is the conformal embedding of SL2 at level 28 and G2 at level 1, so a very fancy one. And then there's this E7 one, and that is the one that you cannot explain via conformal embeddings, but still via this conjecture. So that's but I cannot tell you exactly how that goes. Yeah. But this conjecture I claim is powerful because I claim if you understand graph V, then you can do this. By hand, this is not be able to do that. Okay. And really for the remainder of the 3 hours, I want to talk about SL2. The reason is very simple. It's as I told you, there are very, very few logarithmic conformal field theories that are understood from the vertex algebraic perspective. You can count them using only a few fingers. This is the Westermino written theory of GL1/1, the triplet algebra and its friends. So that is, for example, this the singlet algebra. So Kausch is very well known for studying it. Azad is very well known for studying it. Simon Wood and Sushiga are and all this. And that's it. And then you have the fraction level SL2 Westermino written theory. And I can even recall the histories from the 90s. There was a bunch of physics studies on it, but from maybe from a bad perspective, so that it didn't lead to anything. It was actually, as I said, the yellow book called it intrinsically sick. From a mathematical point of view, there was a very good work already in the 90s by Milash and Adamovich, and then nothing until maybe 10, 12 years ago. David Rideout and I reconsidered it. And basically we noticed that, I think we noticed what the CFT community has done wrong. And then over the last 10, 12 years, many people, that would be more than handfuls of people have studied it. And by last year, the complete understanding of this theory has been achieved. And technology has been developed by that. So from that point of view, I think it makes sense that if I just talk about SL2, okay? So it's also like SL2 always sounds so simple-minded. Maybe it's not. And it also tells you quite a bit how you maybe do representation theory of vertex algebras. You do it, of course, step by step. And so here SL2 is nice because we can start with the finite dimensional Lie algebra, which all of you know by heart. So that means we are in a good situation. I have the usual commutation relations. I just write them down that you know my normalization, and in particular, we also have a linear form normalized in the usual actually not in the usual way. I always forget the normalizations. If we have with a bilinear form, we can always write down Casimir with respect to the bilinear form. We see the dual to H is 1/2H, the dual to E is F, and the dual to F is E. So and then we know from standard Lie theory that once we have an invariant bilinear form of basis and dual basis, then the corresponding pairing gives us a Casimir. So that means an element of the universal commutes every element of the in the center. Okay, I write this here down because this is important. Now, what one does in order to do representation theory, first of all, one simply studies the representations that one can study, and then eventually one tries to argue that this is all, or if it's not all, one tries to find what is missing. And so we will also proceed. So this, and first for SL2, what type of representations do we have? We have the integrable ones. I denote them by LR, where R is the dimension. I think. And so that means in R is the dimension, and it has the highest weight with this convention is then. And these are all the representations that you need if you were looking at the rational theory. But we are not looking at the rational one. And so that means you have to ask yourself, how can I relax these conditions? Well, I can define a highest weight vector of any highest weight. So that means I get modules d plus lambda. And here, if I want to depict this module, I would just draw here our dots indicating the weight vectors, and then the E of SL2 would increase the weight and the F decrease it. Right? And so if I d plus lambda, then just highest weight representation. And just like HW of highest weight lambda. So in this case, we would have here a highest weight vector that is then annihilated, and then we would have weight vectors up to minus infinity. And, so that, again, I could equally well have written here a minus, and minus would just mean that I take lowest weight vectors instead of highest weight vectors. Okay. Now I'll not do this. And now one wants to jog this further, and then the jogging further would be just weight representations. In the CFT literature, they were first introduced, I think, by Alyosha Senikatov, and he called them relaxed highest weight representations. But we decided to drop this because there is no highest weight vector, so then it's a bit misleading to have that word in there. So this, and I call them E lambda and maybe C with an underline around it. And these are representations that have weight vectors, but they don't have any highest weight vectors, so they go to plus and minus infinity. And those, I assume you're not that familiar with those, so let me tell you precisely how to construct them. And then, because there we also will see then for the first time the non-semi-simplicity. So how do you find them? So it has a one-dimensional weight spaces whose basis and the basis I denote by v lambda plus 2n. So here this label refers to the action of the h, so it's the weight label.
So do you need n and 2c or n z because it has 2n?
Oh, thank you. Thank you. Then one can think about it. What does E has weight 2? So what can it do is it can increase the weight by 2. And now you of course want F to decrease the weight by 2, but you also want this to be compatible with somehow with the commutation relations. And if I now simply require F acting on this one gives E lambda plus 2n times 2, that would make sense, right? So what's the trick? I have here this label C, and this is the Casimir eigenvalue. So what we require is that the Casimir acts by a given scalar. Why is that so useful? Because if we think about it, we have the Casimirs in particular. What can we now do is we want to look at the action of F on V lambda plus 2n, but this one is the image of of the weight vector with label 2 less. And f times e you can express in terms of the Casimir and h. You can first of all here use that the commutator of e and f is h, and then rewrite this f times e is equal to the Casimir minus 1/2 h, and then you also get a linear term in h. So in particular, so should I? So and if one does this, one gets here c bar, and then better copy the expression, and then some polynomial that depends on the weight label. Okay. So so here we learn two things. I can define a general weight modules, but in order to do this, I need more information. I don't only need a weight label, but I also need once it says a central character, just a Casimir eigenvalue.
So they're not related. They're independent.
They're completely independent. But we also see here something. We see, okay, E will never have a kernel, right? E on a vector will always be another vector. F acting on a vector will always be another vector times a scalar. But the scalar is given by some polynomial relation between Casimir eigenvalue and weight label. So in particular, if I fix the Casimir eigenvalue, as you asked, that we get a 0 here, then all of a sudden F will have a kernel. That means we'll have a lowest weight vector. So what we see here, we observe that lambda is irreducible unless this expression is equal to 0. And what is it? 1/2 mu squared minus mu. Right, and this is even an expression you know from Casimir eigenvalues of highest weight representations. And plus for mu in this in this whole set of the even integers. And in this case, what do we see here? And if we have this relation, then we have a lowest weight vector. So that means in that case, we have a submodule that is of lowest weight type. And again, I better check what the label is. And we have a lowest weight module of lowest weight mu plus 2. And then if you quotient by this lowest weight modules, then all of a sudden the action of E in the quotient has a kernel. So that means the quotient has is a highest weight. And so it's always
lambda is any complex number. Lambda is any complex number.
And so at the moment, I didn't write what it is, but both lambda and Casimir eigenvalue can be any complex number. Eventually, we prefer to restrict to real numbers.
Oh. So when you fix C like this, you don't get Verma module or contributed Verma module.
No.
You always get a submodule.
If I fix, yeah, exactly. Oh. So here, first of all, structure of modules is well depicted via short exact sequences, which tells us submodule, quotient module nicely what it is. And so in particular, we see here already some indecomposability on the level of the finite dimensional Lie algebra. And this is kind of the starting point. And now one wants to lift these observations to the affine vertex algebra. And also, maybe before I do this quickly, I could give this a label minus here. Because really what I did here is I did a choice. And what I could do is if I do a plus, I swap these two. right? Then of course I have to also here, here of course I would get a minus sign here. Here I would swap these two. Here instead of a minus I would get a plus sign, and here the Casimir relation one can quickly compute will also only change mildly. One gets a plus, one gets just a few plus signs instead of minus signs. In particular, what turns out is, in the construction, one does a few choices. Of course, one chooses the weight labels, but no one also gives E and F a distinguished role. This distinguished role is completely unimportant for generic choices, but whenever you choose this relation between your weight label and your Casimir, then you will either in the minus case, you will get a lowest weight module as a submodule, and in the plus case, you will get a highest weight module as a submodule, and otherwise, everything is very similar. And just to out.
It's always not clear.
Always not clear. Yeah, please ask questions. So this was probably a review, but an unusual review of representation theory of SF2. And now one wants to lift this to the affine algebra, and in particular to the algebra. So this means we go to affine one. So then, first of all, could have kept this. In the affinization, what do? Is I just give my generators an additional mode label n, and then one also adds a central element and a derivation, but the derivation you ignore, and the commutation relations. If I want to write this in a compact way, I would just write it as the commutator now of two elements is the commutator of the corresponding elements of SL2, and the mode index adds up, and then one gets, and the central element appears if n plus m is equal to 0, so m is minus n, and here x and y are our elements of SL2. That is affinization. And if we have the affinization, we can construct Verma modules as follows. When we have our modules of finite dimensional SL2 at hand, and so we can take M to be an SL2 module. Then what can we do is we can lift M to a module of the positive half of SL2 hat. This means by this I mean, well, I only take the positive modes. We are saying that xn acting on m as xn as 0 positive, and k acting on the acts on m via multiplication with a scalar k. This scalar here will be our level. It will be just a priori just a complex number, but we will fix it soon to be rational. So then, then we can define the Verma module in the usual way. And we let the negative part act freely. yeah, this. So you all know this this means we have, for example, we could have started with a finite dimensional module of SL2, the LR, then we would just have all positive modes acting as 0. We require that level x by multiplication with the scalar, and then all the negative ones freely. So that means as a vector space, it's just this finite dimensional module times times modes, times polynomials in the negative modes. Okay. Now, and now one can take the trivial representation, and that deserves a special name. It's called VK2. It is the universal affine vertex algebra SL2 at level K. More precise, it's just the underlying vector space, but it's well known. One can give it the structure of the vertex algebra. In particular, to every x in SL2, you can define a field. Maybe I'll write down the most important fields. So most important fields are the ones corresponding to the polynomials x minus 1. And it's just this field. And for example, it's fairly easy to compute that the commutator of the field x corresponding to the element x in SL2 with another field y is exactly given by that the commutator gives you the field corresponding to the commutator times the formal delta distribution, and this level appears as a derivative of the formal delta distribution, which is then completely equivalent to the usual OPE formula vertex algebra. Okay. Now, so now, in particular, via this Werner module construction, we have a functor from modules of finite dimension SL2 to the affine algebra. And now one wants to know whether these are also modules of the affine vertex algebra. The answer is yes, if we consider the universal affine vertex algebra, but not if we consider its simple portion. So, the vertex algebra needs not to be simple. But in fact, it turns out that it is simple. It's always simple if K is rational, and if it's rational, sometimes, sometimes not. Then you have, if it's not simple, you have a maximal ideal, and you set LK_SL2, also put the K as an upper index, lower index, as this motion by the maximal ideal. This maximal ideal is unique. And this is called the simple affine BOA SL2 at level K. Okay. And now I can tell you what a module of the affine vertex algebra is. A module of the affine vertex algebra is the same thing as what is called a smooth module for the affine algebra. at level k. So level k means that the central element acts by k, and smooth means smooth is something very natural. See, one has to do with a formal power series, and one wants that if one acts, that these become formal long series. And for this, one needs that sufficiently positive modes eventually always annihilate a given vector. And this is exactly the smoothness condition. Means that means for every vector in a given module, let's call it M. Smooth means that
V is M. V is M.
V is M. Yeah. It's always so hard to remember what you did a while ago, right? Okay. And so this means understanding representation category of the universal affine vertex algebra is something very clear. The problem is with a simple quotient. So the problem is really, this is just too huge, and it won't have a structure that you want to study, that I do want to study. And usually you prefer to study the simple quotient. And so a module for the simple quotient is a smooth module. So I write a module for the universal affine VUA that has the property that it's annihilated by this ideal of the universal vertex algebra. And this is now the problem, right? Now you have to understand which modules satisfy this property.
And is N upper K also the same as N lower K?
This is so complicated. Yeah. Oh, no, I'm sorry with notation. I always forget what I write.
So why use, I mean, wouldn't you just call this like positive energy or truncation condition? Why call it smooth again?
Why?
This terminology of smooth. It's just some annihilation condition that you would normally
yeah,
call.
it doesn't sound so super natural. I forgot why it is called smooth again, but it's I would have to look it up. By Frankel and Ben Sweet, they explain it, but I forgot.
So as an example, I mean, if you take the image of one of your Verma modules under spectral flow, it is smooth, but
yeah.
Does it fail the second condition?
Yeah, I'll come to your question. Just wait 5 minutes, okay? So now, so what I want to present is I'll list you what these modules look like, and then hopefully I'll also tell you more structure and also maybe give you ideas about constructions and techniques. Yeah, in particular, I will come to your question. So the point is now what one would like to order the problem. So one wants to here really just do representation theory of an affine algebra. And so here one defines first of all categories to give it a little bit an order. So here the largest category that we want to consider we call the weight category, the category of weight modules. So weight modules M, so that means So what do we want? M is finitely generated. And it admits a weight space decomposition. That means we can write it as a direct sum of weight spaces. And what do we mean by a weight space? This contains all elements in the module on which our H0, the one corresponding to the Cartan subalgebra, acts by the corresponding weight. And we would like to act L0 by delta, by the conformal weight delta. And we prefer to write it like this, because we don't want to require that L0 acts semi-simply, but it should act at least with finite dimensional Jordan blocks. And then, moreover, one requires that each weight space is at least finite dimensional, each bi-graded weight space. Okay, this is so these categories are a little bit technical, but I define first now for categories, and then I'll give you examples, so then you exactly see which modules belong to us. So in this smoothness, I require that Xn eventually annihilates vector, but a given vector, but the n depends on the choice of a vector. In particular, the spectrally flown modules will be in our category, but they will not be in the subcategory that I now define. This is the subcategory of the previous one of lower bounded modules. That means that the m lambda delta vanishes if the conformal weight is too small. Since I didn't require conformal weight to be real, if the real part of the conformal weight is below a certain bound. And these are precisely the modules that you get via the Roma module construction of 5 minutes. These are precisely the modules that you get via this Roma module construction. And then, thirdly, you have the category O. So, this is the subcategory of the previous one. Such that each delta, each conformal weight subspace, each conformal weight subspace is a module for finite dimensional Lie algebra is in the category O. So that means here, so category O is the category of highest weight modules. And then finally, the last one is the category that gets a label KL for Kashtan-Buschlik, and this is the subcategory of the previous one. Such that each conformal weight space is integral. It's a finite dimensional module for SL2. Okay. And then now one can construct examples. And maybe so I think next lecture I will, before the lecture, write down these definitions again, recall them, and then I will slowly give you example for example. But to give, but where we want to, yeah, why don't I stop? This doesn't make sense to start with the examples now. So that's then but let me maybe just give you an outline. So next lecture I will recall these definitions, and I'll give you examples for each category, and in particular you will then see the spectral flows, and then I will be able to tell you what all irreducible modules look like, but we still have a very difficult problem of studying of constructing indecomposable modules. So one also calls logarithmic modules. And I'll give you a new construction of those that is, I think, very simple. And then maybe I go to introductory structure or other things. Actually, please tell me if there's anything you'd like to hear. It's just the warm up. My next lecture is next week, so I've got plenty of time to change plans. Anyway, thank you very much for your attention.
So maybe we have a time for a quick question.
So we're interested in the logarithmic, where L0 is acting with generalized eigenspaces instead of eigenspaces. The weight modules, we always have that, you have this Heisenberg running around that is acting as, so everything is eigenspaces with respect to that.
Yeah.
Is it of interest to make that action be a generalized eigenvectors instead, or is it just too complicated to do?
You can do that. And
But nobody does.
Hmm?
Nobody does.
So actually it would simplify things. So the problem is you wouldn't get a block with finite category anymore. So you'd have infinite length objects, which for technical reasons you might not be too pleased with, but the classification is all of a sudden much simpler. And getting a tensor category structure is no problem. Get it equally well. So everything works equally well. You just have to ask yourself why you want to do it.
For example, you will not have projective covers.
Yeah.
You will not have enough projective covers in the category, so it's hard to work with.
But that's okay, right? That's what's in fact. So physics is interested in it. They like these line operators acting on topological boundary conditions, and they are interested in these big categories.
In what?
They are interested in these big categories. So, but it's really just a convenience not to do those. You could do it, but if you want to have a locally finite category like Azad,
it's very complicated. Yeah, the answer is very complicated.
I don't think it's so complicated.
Okay. If you want to understand classify modules, or if you want to understand structure the category, it's very complicated. It's a category, not, as you said, even non-locally finite.
Yeah. So as a conformal field theorist, you wouldn't want to do. But I come back to what you say in next lecture.
Okay, I think it's time for lunch. So let's say. So who have not the tickets yet are here.